assume I only have eight inodes and 8 data blocks, 0 through 7. And let's assume that the file occupies in the data block from 4 and 5, or 4 let's say. Block number 4 in the, so therefore I will have 0, 0, 0, 1, 0, 0. So this is your data block. Okay. Right. Now, remember in the case of, without looking at the tree map, I told you that when you want to add an additional file or a block, you will have to go and modify all the directory entries and everything else. But let's assume for the time being we just have one file which I have to update. So let's assume I want to append some data to the file that I have. Correct? So let's assume I want to create additional data block to the file. Okay? What are the write operations I have to do? I want to append one disk block to an existing file. I'm not creating a new file, but I am appending one extra block to an existing file. So what all I have to do? How many writes I have to do? I have to write one here. Then I have to update this guy. Then what else I have to do? Update the inode saying that it says 4 and 5. Correct? So right now just appending one byte to an existing file will require 3 write operations. Okay? Now, let's look at what happens if something crashes. Okay? So remember, these are 3 operations. These are not atomic. All 3 I don't have atomicity. I can only write one disk block at a time. So let's assume I have written a data block has already been written to the disk. Okay. Then it crashes. System crashes. When I come back up, what's the issue? What's going on? So let's okay, hold on. Let's make sure that I have, this is the state of my file system. I've written the data block 5. I have not updated the free list. I have not updated the inode, and the crash occurs.
It will be as if the write never happened.
Yeah. So all will happen is that your work is wasted. Whatever you did, you didn't save. Whatever work you did is gone. Fine. File system itself is consistent. Nothing has happened. Okay. So that is scenario 1. Now, let's look another way. Because remember, when I have written something to the file, I'm giving to the disk scheduler hey, here are the 3 blocks that I want to be written. Based on the kind of algorithm it has, it could have reordered the blocks depending upon to minimize seek time and so on and so forth. So now what would happen? So case 1, disk block 5 is written, system crashes, you all said, file system is consistent, my work is gone. Now let's look at case 2. Inode is updated. Inode is updated, meaning I have saved the fact that an additional block exists in this particular file. So case 2, inode updated and then crash. And the system crashes. Now what? So now when you come back up, What one?
So other file can technically use that block.
Yeah, so this file, even though legally you have access to block 5, but there's garbage there. Not you are taking, some garbage is there, right? So that means the file is corrupted. Right? So, okay, so this is, we'll have to do all the, that is where the file system check and all that. So case 3, now, case 3, bitmap is updated. Okay, that is, I have written the fact that block 5 has been allocated to this file. So I updated the bitmap to reflect the fact that 5 is no longer available. Then crash occurs. Now what?
We lose the data block.
Sorry?
That data block becomes useless.
So this is basically an orphan. Okay, so that means what I have to do, so when I come back up, if I want to run eventually, there may be a lot of orphan blocks. 5 is already allocated, but it's not being pointed to any of the inodes. So when I run my consistency check, I have to go through the bitmap, make sure that that particular block is accessible to some inode. If not, that needs to be reclaimed back into the tree list. Okay, so that is what your FSCK does. But for huge disks, going through that entire inode system is very expensive operation. Okay? By the way, one of your PhD students, Professor Kannan student, has come up with a very efficient, David Domingo, a very nice paper with recent OSDI on how to do this very efficiently for large disks. So in general, it's a very slow process, because now, remember, this I have only shown you 7 bits, right? Disk capacity is increasing, block sizes are increasing. Of course, you can increase the block size to reduce the number of bits in the bitmap, but still, for huge capacity disk, terabyte disk, etc., it's a lot of work to reclaim all these orphan blocks, okay? Because you don't know how many of them were in this state, right? Let's say there are only 3 orphan blocks, you still have to go through every block to make sure that it is not retrievable from some inode. I have no idea which one is an orphan, so I have to literally sweep all these blocks. So there are some techniques that you could use, but I just wanted to make sure that you understand that file system consistency is still an open problem. We have to still worry about all that. So this is fine. Super block, not much metadata is there, and we need to worry about all that. So now, what we will do, we look at two advanced file system. I borrowed some slides from Professor Kannan on this. So, if you look at a traditional Unix file system, right? Read performance and write performance. Okay? Both of them require a lot of seats. That's because, why? Because inodes are in one place, all the data blocks are scattered all over the disk. So you will have to first access inode, go to the data, inode, data, inode, data. This going back and forth between metadata and data will degrade performance significantly. This can be mitigated, right? You're not doing this kind of inode disk every time. Only for the first time, then you can always cache it in your buffer cache, so that any subsequent read access to the block will not have to go to the disk. Okay? So you can definitely improve performance by using a buffer cache. Meaning, once you have gone through the traversal of the path, once you have gotten the disk block, any subsequent seek within that block will be in memory already. So that you can worry about it. And of course, larger the block size, more data is going to be cached in the buffer cache. So that any seek within that 4K, you don't have to go to that. So that we can mitigate. But for write, we are paying, because you will have to update inode, update data block, update inode, update data block. Okay? And especially when you create a 1 byte file, you'll have to go to the parent directory to update the last modified time as well, because now you're adding a new entry into the contents of the parent directory. So therefore, this one still seek performance, rather the amount of time it takes to seek the blocks, it kills performance on the write. I cannot mitigate that. You can mitigate a little bit, that is saying that, hey, I won't write all of them, I think I can do that together. But then, of course, if you cache too much, if you crash, you will lose a lot of work. On the other hand, when you sync, you still have to write all these blocks to the file. So, a lot of interesting approaches have been taken into the file system. First one, we will study the fast file system, which are now part of all Linux and 4.3 BSD and so on and so forth. And then we'll see a research paper on the log structured file system. Okay. So what are the things that we could do to improve if you look at the basic layout, right, some bitmaps, some inodes, at least these two are close together, that's not a problem. But the data blocks are scattered all over the place. So therefore, anytime you will have to access a data block and go back to either access the inode or the bitmap, there will be tremendous amount of seek time. So therefore, you want to minimize that. So if you want to create a file within that, you'll have to read the inode, read this inode, read the data of the inode, then again read this, read this. So if you look in time, first you read the inode, read the contents of the inode, read the subdirectory, read the contents of the subdirectory, and so on. So as long as inodes and data are separated, you will see this back and forth, and eventually you will have to write the read the inode bitmap, update the bit, and then flush it to the disk. You will have to read the inode because you'll have to update, because remember, you're adding a new content into the file, so you'll have to read and modify the last part of the text. All right. And then you'll have to update the size, etc., etc. All right. So now, what I will have to do? Okay. Another one would be how to choose the inode, right? If the inodes are in one place, hopefully this data block, the new data block you have created is somewhere here for that file, right? If you had a choice, there are so many inodes all over the place, then hopefully you can be smart enough to choose the data block to be on this guy, let's whatever, this was block number 8, this may be block number 16. If you knew that this was in one track, the other one in one track, then the amount of seek time will be very small. In general, it's not that easy to choose this kind of stuff, right? This is fine. What about another guy somewhere there? It's not clear that this inode will be free at this time, right? This data block may be here, the free list may be here, you may want to look for something there, right? So therefore, what you want to do is, whenever you create a new file, not an existing file, you will need one inode, minimum you will need one data block. Okay. So if you really want to minimize seek time, what you want to do, then you have to go through all the inodes and find out where it is laid out and pick that bit, that inode, instead of randomly picking any inode, right? So remember, you have your free list, right? This is your inode bit map. Instead of just looking at any bit is available, what you want to do is find the data block, right? And find the inode that is closest to that particular data block. That is one way to reduce the amount of time it will require to create a new file in your file system. The other one, the other approach that is taken in a file system is to keep the inodes very close to the file system. So instead of having all inodes in one place and having data blocks in another place, one approach would be to do smart allocation. In other words, choose the inode which is close to the data block. Okay, if at all it's possible. The old file system, right, where you had super block, all the inodes were in one place and the data blocks were scattered all over the place. Believe it or not, because of that movement between data block and inode, data block and inode, data block and inode, only 2% of the disk bandwidth was possible because of the seek time. Obviously, that's not a very good approach. So instead, what people have done, and this I've already told you. Okay. First thing is, we could double the block size. The Unix file system, the first thing people did was to double the block size. Obviously, performance doubled. Because you would need less single indirect blocks. And also, since the block size, like say from 1K it went to 4K, or from 2K it went to 4K, etc., you had more in the buffer cache, your hit ratio would also go up. Okay? So the Unix file system, first is smart allocation. Second is, it's not that easy, but doable. Second is increased block size. Now, the third one, increase block size. Another thing would to have multiple inode extents. So in other words, so one smart allocation. There's a lot of limitations because you will not necessarily find the inode that is very close to the data block. In double or increase block size. But then this has a problem of internal fragmentation. Number 3, partition inodes. Okay. What do I gain? If I did this way, right? Hopefully, the inode and the data blocks have very close to each other. So when you even look at a circular, right? So let's assume every track has some number of inodes, and then the data block, etc., etc. Hopefully, I can allocate one inode here and the data block on the same track. Okay. Now, if I did that, now what is the problem now? What is the difference between having something like this versus this?
You don't know which one your inodes are.
Sorry?
You don't know which inode block your inodes are.
So that means what do I have to do? See here, if I knew the starting address of where the inode started, if I know the number of inodes per block, you give me an inode number, I already know which disk block to go to. Now here, if you give me an inode number, I don't know which disk block to go to. So therefore, I need to maintain a map or a table. So that means I need another data structure called inode map, which tells me, given an inode number, which disk block has to be there. Now where does inode map has to be? Where do I have to store this? Because remember, this is like a major metadata that I have. So that also has to go somewhere in the disk block. So therefore, before the super block, I will now have to have an inode map. That has to be periodically returned to disk. Correct? Because as inodes get allocated and moved, I'll have to update this guy as well. So this also has to be stored somewhere. So this also requires periodic syncing, and you can do this. So these were all the changes that were done to the Unix file system. But one last addition to the Unix file system was fragments. Okay, so far so good. Fourth one was the support of fragments. Okay, what do I mean by that? Remember we said, well, you can improve or double your performance by increasing the block size. If you increase the disk block size, what was that? 1 second. Second idea was was to increase the block size. So for 4K block size, right, the performance doubles, so to speak, but then you had internal fragmentation for small files. Okay. So then the fast file system, Unix file systems, try to support allocation at a smaller than block size called a fragment. Remember, in the Unix directory, for the time being, assume we have direct blocks. You have one direct block points to a 4K block. Now, let's assume your file is only 1K. Okay. So then what you don't need the entire 4K block. So then the Unix file system began to support fragments. So let's assume you have a 4K disk block. That means you can have up to 4 fragments of each 1K. Now, this is your, let's say this is block number 84. Okay. And then only the last block in that file will have a fragment. So let's assume this is block number 84. It will say 1 dash dash dash. So this is your fragment bitmap. Okay. What does this mean? That means the file resides in block 84, but the first 1K bytes belong to the file. Okay. For the time being, assume all these fragments are free in the. So that means now, in the bitmap, I have to have another bitmap also. In addition to the inode map and the data block, I also have to, for every block, I have to maintain fragment bitmap as well. Which fragments have been allocated and which fragments are free. Now this is block number 84, my file size is 1K. Right? What if I have created a file of 5K? What would happen? So the block number 84 is up to 4K. Now what I will do, I will create another block, let's say this is 96. Then this fragment bit will tell me that this file, all 4K of block 84 and the first fragment of block 96. It doesn't have to be always the first fragment. If your fragment bitmap is something like this, means 4K plus 1K of block 96 fragment number 2. So now, let's go back to this 84. Okay. So now let's assume I only have 1. Okay. This is block number 84, and this is the block number 84 free disk, right? Taken, available. Okay. So this is your free list. Free list or fragment bitmap, okay? Let's say this is a fragment. Now, I have 1K. Now let's say it goes to 2K. Okay? So let's say I can allocate here. Okay? Now, let's say these 2 fragments were allocated to some other file. Okay? So now that guy, let's assume. So there's another file. He was allocated. He's also allocated his 84. But let's assume he has 2K worth of data. What will his inode look like? Dash dash 1. Okay. So this is block 84. He has fragment 3 and 4. I have 1 and 2. Okay. So far so good. And now what will the free list look like? Bitmap for block 84. 1, 1, 1. All of them are allocated. Okay. Now let's assume I want to grow this file. One more block, whatever. I can't get one more fragment in this block. Whatever. I have to get a completely new block. And then that new block will have how many fragments?
You copy these two.
What he's saying is right? Remember, why can't I have this like this and 85 like this? What is wrong?
Too many fragments.
For every block, I will have to maintain a fragment width, right? And your inode size will grow, and that metadata will be bad. So what the Unix file system does is that you are not allowed to have, apart from the last block in the chain, you can have fragments, and you are not allowed to have fragments across blocks. So now, in this particular case, all four are full. I want to grow by one more, 1K extra. So what will happen now is that I will be allocated a completely new block, whatever, 96. I will have. Okay. And that 84 will go, this I will copy. And sorry, yeah, here, this will become instead of 0. And 96 will have 3 raised to 1. Okay. So always, no matter how many blocks you have, multiples of 4K, you get the entire block. Only the last block, if it is not a multiple of the block size, then you can get fragments. Okay. So 8K, I will have 2 direct blocks and no fragments. 12K, 3 direct. Any multiple of 4, but any fraction of that particular 4K, and always applies to the last block, because I only want to maintain one fragment. Otherwise, it becomes very messy. Your inode will grow. Okay? So therefore, to avoid internal too much of internal fragmentation, the Unix file system double the file system size, sorry, the disk block size, but allow allocation of less than a block called a fragment. And then they had the concept of a fragment bitmap in the inode, and also maintain a free list, not in terms of disk blocks, but in terms of fragments. And the allocation also was done in a fragment, at the unit of fragment. So if you want 4K, the guy would assign all 4 bits of a particular disk. Yeah? Yeah? So compared to where we are now, there are a lot of improvements that are done. So this is one of them, fragment allocation, disk blocks. And remember, as the capacity of the disk increases, the block size of the disk can also increase. But because of these fragments, you can reduce the internal fragmentation. So for example, you can, if you have a 4K disk block size, you can have a 1K fragment. If you have an 8K, you could probably have a 2K. But remember, this was all when our disk size was G. Now most disks are terabytes. And also, even though everybody has moved on to SSDs, but still high capacity drives are still magnetic drives. So therefore, all these improvements that have been done to the Unix file system, increasing the block size, doing sub-block allocation, having this concept of fragment, etc., has improved the performance of the file system considerably. What I will do in this whole improvement thing is that next what we will do is, this is the Unix fast file system. Lot of improvements done here. Inode partitioning, fragment allocation, etc. After a break, we will look at another improvement that people have worked on, which is the block structure file system. 130. I'll stop here and we'll take it. So does anybody to collect their midterms? Will it show up on class?